In this video, I wanted to talk about torsion. So if you search for torsion in the PE handbook, there's two main equations that you're probably going to end up using. So the first is that the shear stress due to torsion equals the torque times the radius divided by J, and J is the polar moment of inertia. And a key word for this is actually area moment of inertia. So if you search for area moment of inertia, and then you look at the circular cross section, there will be a value for this. And so for circles, J is pi times radius to the fourth divided by 2. And then this R here is the radius to your point of interest. And then T is torque, like I said. Then another important equation is I call the angle of twist equation. So the angle of twist equals torque times the length divided by G times J. So this J is the same as above, and this G here is the shear modulus of elasticity. So this G should be given, and then you'll have to solve for J, generally speaking. Okay, so I have a practice problem here. So a shaft is driven by a 20 horsepower motor at 180 RPM. The shaft has 3 gears. Gear A removes 10 horsepower, Gear B removes 4 horsepower, and Gear C removes 6 horsepower. Find the shear stress and angle of twist in each section. Use the relation horsepower equals torque times N, which is RPM, divided by 63,025. So this equation is in the handbook. If you search for the keyword horsepower and then click through several of them, this will come up. It's important to note N is in RPM and T is in inch-pounds. The shaft is 1 inch diameter and is made of steel with our shear modulus of elasticity equal to 11,600 KSI. So at our motor here, we have 20 horsepower. Then at gear A, we're removing 10 horsepower. So this is going to be going in the opposite direction. At gear B, we're removing 4 horsepower. And at gear C, we're removing 6 horsepower. So just looking at this, I'm going to call this point here D. So this is, I can tell this is kind of going to be a long problem, because we're going to have to go through each of these sections, and we're going to have to find the torque in each section, and then use that to solve for the shear stress and the angle of twist. So a commonality that we'll need for all of these is J. So I'm just going to do that, solve that right now for one time, and then use that throughout. So we'll have J equals pi times R, which is half an inch to the fourth, divided by 2. So 0.09817 inches to the fourth. And I'm doing this just so I don't have to type out this equation every time I go to solve for something. So if we look at section here, DA, do that section first. So what you do to solve for the torque in each of these sections is you pretend like you're looking straight down the beam. So we can draw like a little eyeball here. I'm looking straight down the beam. And then we're going to make a cut in each section. And then you can look at either side of the cut, but we're just going to do whatever's easiest. So I think the easiest thing is going to be to look at the left side of each cut. So starting with DA here, what do we think the torque is in here? Well, if we look at the left side of this cut, we only have one torque here, which is from our motor. So if we use this equation up here, rearrange and solve for torque, we can go ahead and find the torque at D, which is going to be the torque all the way up to point A. And since that's the torque in this entire section, that's what we'll use to solve for the shear stress and the angle of twist. So we have 20 horsepower, and we're at 180 RPM. And this is going to give us an answer in inch-pounds. And like I said, this equation comes from the handbook. So that comes to 7,002.78 inch-pounds. And so if you, I already mentioned this, but if you search for horsepower and then click through a couple of them, you'll come to this page. It'll tell you what the units are for each of these. But that's an important one to know how to look for, because it's not going to give that to you in the problem. So this is the torque in section DA, is 7,002.78 inch-pounds. So now let's solve for the shear stress. So if you remember from our equation above, that is the torque times radius over J. So our torque is 7,002.78 inch-pounds. And then our radius is going to be half an inch. And then over J, which is 0.09817 to the fourth. And looking at the units, that's going to give us PSI, which is what we want. That's going to be 35,666.59 PSI. And then let's go for the angle of twist now. So the equation for that is T torque times the length over GJ. So this length here is the length of the section that you were looking at. So for this first section, it's going to be 6 inches. So we got 7,002.78 inch-pounds times 6 inches. It's important to note this is going to give you an answer in radians. Times 11,600, 10 to the 3 pounds per inch squared, times 0.09817 inches to the fourth. It's going to be 0.0369 radians. And so if we want to convert that to degrees, we know there's 360 degrees per 2 pi radians. So that's going to be 2.11 degrees. So that is our angle of twist and our shear stress in that first section, so between the motor and gear A. So now we can look at A, B. So if I'm looking down this beam, or this shaft here, when I get to section A, B, now I have 2 torques that I'm looking at. So I have this one from the motor, and I need to subtract out this one at gear A. So at the motor we had 7,002.78. Subtract out of that the torque at gear A. So that's 10 horsepower. It's going to be the same speed, so 180 RPM. So that's going to be 3,501.39 inch-pounds. And that, again, that makes sense because we're removing half of the power. So this should be half of that. That's just a spot check. So our shear stress is going to be 3,501.39 inch-pounds. and we're going to multiply that by half an inch, which is our radius. Divide that by 0.09817 inches to the fourth. So that comes to 17,833.3 psi, which again, that makes sense because it should be about half of that. And then for our angle of twist, we're going to have 3,501.39 inch-pounds times the length of that section, which is 2 inches. And then we're going to divide that by G, which is 11,600 10 to the 3 pounds per inch squared, times our J, which is 0.09817 inches to the fourth. It's going to be 0.00615 radians, which is going to be 0.35 degrees. Now that's a lot less than half of this, but we have a much shorter section here, so that makes sense. Now sometimes it might ask you to find like the cumulative angle. So in that case, what we would do is, after finding this angle here, 2.11 degrees, we would just add to that this 0.35 and get the cumulative angle at AB. But all we're asking for is what the angle twist is in each section. So that's an important thing to differentiate out. Okay, and then our last section here is BC. So if we again look down, we have 20 horsepower, then minus 10 horsepower, and then minus another 4 horsepower. Or we could look at it going this way and just use this 6 horsepower here. So I'm going to go ahead and do that to get my torque. So times 6 horsepower divided by 180 RPM. It's going to be 2,100.83 inch-pounds. And solving for our shear stress, 2,100.83 inch-pounds times our radius of half an inch. Then divide that by our J value. Can be 10,699.96 psi. And that should be about 0.6 or 60% of our torque in AB. So that makes sense. And our angle of twist, we're going to have 2,100.83 inch-pounds. Times the length of that section, which is 4 inches, divided by GJ, so 11,600 times 10 to the 3 pounds per inch squared, times 0.09817 inches to the fourth. Sorry, I entered that wrong into my calculator. Let me redo that real quick. Okay, so 0.00738 radians, which is going to be 0.42 degrees. Okay, so we found the shear stress in each of these sections, and they're all different. They should all be proportional to each other though, which they are. And then we found the angle of twist in each section. So we know when we look at A versus D, A is 2.11 degrees out of phase. And then when we look at A and B, we know that B is 0.35 degrees out of phase from A. And then from B to C, we've got a 0.42 degree difference. But yeah, keywords are very important for this type of stuff. So torsion is a good keyword to search for. That's going to help you find these equations. And then for this equation here, a keyword for that's going to be horsepower. And then for your polar moment of inertia, that's going to you're just going to search for area moment of inertia. Let me make sure. Yeah, that's in the same column as area moment of inertia for a circle. It's just down the bottom of that box. But yeah, I hope this helps.